Yeah, hi. So I'm going to talk about shape analysis for functional programs today. So I'm going to talk about orders in trees just as Connor did, but in a very different sense. So traditionally, shape analysis in imperative setting is primarily concerned with either discovering or verifying shape of a pointer into memory. Functional languages, we have type systems with algebraic data types that let us imagine shape of a data to determine its type. So if we know that the type of a data is an alpha tree or an alpha list, we would simply recollect the inductive type definition of an alpha tree or an alpha list in terms of the constructors to imagine the shape of a data in memory. So the types could also let us document the shape invariance of functions. For example, a function f could expect a tree, the shape of its argument to be a tree, and might expect to return a result whose shape is a list. The type of a function could document this particular shape invariant in its type. So, however, function f could give a more stronger type shape invariants which are not captured in this simple type of f. For example, f can be a function which traverses a tree and produces a list of elements. Consider a tree that contains elements from x1 to x5. So, f can be a traverse function which visits nodes in the tree from x1 to x5 in the order as indicated by the red dotted line. While it visits every node in the tree, it produces a list of elements in the same order as it visits them in the tree. Therefore, the order in which the function traverses visits nodes in the tree is same as the order in which the nodes appear in the list from left to right. So if we indicate the former with the red dotted line and the latter with the blue dotted line, and we call them as in order of T and forward order of L respectively, and we have the invariant, the in order of the tree T is same as the forward order of the result list L. Definitely the type of traverse, the simple type of traverse did not capture this particular shape invariant. So we asked the question of can we refine ML types in order to express these sort of rich relationships among data, shapes of the data, and automatically verify them against the implementations. So this is the question that we consider in this paper. Specifically, we are interested in a refinement type system to let us capture not just the assertion that a function accepts a tree and produces a list, but also that the shapes of the tree and list are related in a well-defined way. So in order to relate the shapes of these disparate data structures, we need a common language that let us talk about fine-grained shapes of data structures such as in-order, diffuse, post-order, and so on. So if we take a closer look, we observe that all of them can be expressed as relations. So we have developed a language based on relations and relational algebra that let us express these fine-grained shapes so that the predicates or expressions of this language let us denote the assertions or shapes of data structures. So if we take the predicates and define types, ML types with these predicates, we have types which would let us, which capture not just the simple assertions, but also more complex shape assertions or shapes of data structures. Let's take a look at an example. Consider a tree again that contains elements from x1 to x5. The in order of the tree T is a binary relation that relates elements in tree T, relates x1 to x2, x1 to x3, so on until x4 to x5. So if we denote the in order of tree T with Ri of T, we have Ra of T as a set of pairs xi, xj, so that I is less than or equal to j. Likewise, if you consider a list L that contains elements from x1 to x5, we have forward order of L as a binary relation that relates x1 to x2 and so on until x4 to x5. And if we denote forward order of L by Rfo of L, we have the set of pairs, the same set of pairs xi, xj, so that I is less than or equal to j, where xi and xj are drawn from the list itself. So we observe that if list L contains elements of tree T in order, we have the forward order relation of list L being denoted by the set there is same as the in order relation of tree T as denoted by the set of pairs. So we make use of this observation to write a type for traverse, where we say that traverse is a function that takes a tree and returns a list where the forward order of the result list is same as the in order of the input tree. So we refer to this type as a relational type of traverse. Similar to the in order and forward order relations, we can also consider unary relations such as tree membership relation and list membership relation that denote set of elements in the trees and lists respectively. So if we let Rtm denote the tree membership relation, then for the tree T shown, Rtm of T is a set of elements from x1 to x5. Likewise, if we let RLM denote the list membership relation, so RLM for the list L shown is a set of elements again from x1 to x5. So these sort of unary relations also let us express shape invariance of data structures. For example, if we let the left branch of the tree T be named LT, then Rtm of LT is a set of containing the elements in the left subtree from x1 to x3. Now, in order to make the assertion that every element in the left subtree precedes the root element in order, we'll only have to say that RTM of LT, or the tree membership members of LT, cross-product with X4, is a subset of Ri of T, where Ri of T denotes the in-order relation of the tree T. So the language of relations with these relation operators such as union and cross-product is capable of expressing fine-grained shapes. So the equality and subset inclusion predicates, or these kind of relations, let us express shapes of data structures. For example, the traverse function, where we have seen that RFO relation of the result list is related to RIO relation of the input tree. And these relations, RFO, RIO, and so on, can be constructed from a small set of primitives such as identity relation, null relation, equality relation, and so on. Therefore, we have a very expressive type refinement language. However, in order to ascribe shapes to polymorphic higher order functions, so that they'll be able to relate not just a couple of shapes of a couple of data structures, but also they are general enough to relate shapes at different shapes at different call sites. They need to be more general than we need types that are more general than that are able to relate a couple of shapes of a couple of data structures. For example, we have an ID function, which is an identity function, and a treefold function, which is a simple fold function over trees. So these are polymorphic functions that are defined in terms of type variables alpha and beta. So these type variables can be instantiated by different concrete types at different call sites. So the relational types of ID and treefold must be general enough to relate these different shapes at different call sites for different instantiations of alpha type variables alpha and beta. So let's take a closer look at the identity function. We know that ID is agnostic of its shape of its argument, that is, it can take arguments of different shapes. However, regardless of the shape of the argument, whatever is the shape of the argument is also the shape of the result. So if we denote the unknown shape of its argument by an abstract relation rho, then we can use the abstract relation to write the type of ID as a function that accepts x of type alpha, produces a y of type alpha, such that the shape of y as interpreted by the abstract relation rho is same as the shape of x as interpreted by the abstract relation rho. Observe that the abstract relation rho is generalized in the type of ID. So the rho is actually relational parameter to the type of ID, just as an alpha and beta is a type parameter to the type of a type variable parameter to the type of ID. So we call this particular type of ID as relationally parametric type of ID. Similarly, for the treefold function, we could ascribe a parametric type that relates some relation over the input tree to another abstract relation over the result beta. Let's consider a use case. Consider a traverse function which is written in terms of a treefold function. Treefold folds a tree from left to right in pre-order. So traverse function can be written in terms of treefold. Likewise, a make tree function which can be written in terms of treefold, traversing the tree and producing a new tree that contains the same set of elements. Likewise, the least k function which produces a list of elements, the k list of elements from the tree can be written in terms of treefold. So a parametric type of foldal can relate abstract membership property of the result type beta to the concrete tree membership property of the input tree T. So if we denote the abstract membership property of beta as with help of an abstract relation rho m, then we can have the type of treefold give us an invariant that relates the rho m of v, which is rho m interpretation of shape of the result v, being same as the RTM or the tree membership property of the input tree T. So how is this type useful? So reconsider the traverse function. You could instantiate the abstract relational parameter to treefold the concrete relation RLM, which denotes list membership relation, where the instantiated type gives us the invariant that the list of the set of elements of the list membership property of the result list is same as RTM of T, which denotes the tree membership property of the input tree. Likewise, for the make tree function, you can instantiate the relational parameter with the RTM or the tree membership relation to derive the invariant that the result tree contains the same set of elements as the input tree. On the other hand, if you try to instantiate the relational parameter to treefold with the list membership relation in least k function, the resultant instantiated type would not type check the higher order argument treefold, and as a result, it rightfully denies us the invariant which asserts that the list of elements in the result list is same as the set of elements in the input tree. Right. So ID and treefold are functions parameterized over relations. We can similarly have relations parameterized over other relations, which we refer to as parametric relations. So what does it mean to parameterize a relation over another relation? Consider an example with the tree T. So we have seen that Ra of T, or the in-order relation of tree T, the set of pairs such that it's a relation over elements in tree T. You can generalize Ra of T, or the in-order relation, to row parametric in-order relation, which is defined in terms of an abstract relation rho. So the row parametric in-order relation, instead of relating elements of tree T, would relate the row interpretations of elements of tree T. Therefore, it relates different substructures of elements as defined by the abstract relation rho. So the row parametric in-order relation is strictly more general than the non-parametric in-order relation, in that if we instantiate the parameter rho with a trivial identity function, we get back the non-parametric in-order relation. Consider an example. Consider a tree T that contains pairs. We have seen the Ra of T is the set of relates the elements in the tree T, so it relates pairs in the tree. Row parametric Ra of T relates row interpretations of pairs, so it's row of xi yi to row of xj yj, where xi yi and xj yj are pairs in the tree. So if we let RFST be a relation such that RFST or a pair is a singleton set of its first component. Now if we instantiate the parameter rho in the in parametric in-order relation with RFST relation, we get a relation that relates first components of pairs in tree T. So in effect, we have a relation that relates that's more general than that actually defines a more finer shape than a simple in-order relation over a tree T, which only relates these elements in the tree. Now consider an example where we map these tree of pairs to tree of first component of pairs using a tree map function, which takes a pair projection function as its hierarchy argument. Here we have the invariant that the in-order among first components of pairs in T, same as in-order among elements of the pairs in T prime, elements in the T prime, sorry. So the application of tree map to T and FST has to satisfy this invariant, which means that the type of the tree map itself needs to be more general in that it needs to relate in order among any substructure of elements in alpha tree, where alpha tree is its input, to in order relate that relates some other substructure of elements in beta tree, where beta tree is a result of tree map. So how do we express this invariant? So this is where we can use parametric relation to write the type of tree map which has a post condition that relates the parametric RA relation of the result T prime, result tree T prime, to parametric in order relation of the input tree T, where the parameterized relations describe the in-order relations among the trees that relate different substructures of elements rather than just the elements. So these rho beta and rho alpha, which are used in the parametric relations in the type refinement of tree map, are generalized in the type of tree map as relational parameters to tree map, just as we did for the identity function. So far we have seen a relational language that is capable of expressing shapes. We have seen that functions can be parameterized over relations in order to type parametric, polymorphic and higher order functions. And relations can be parameterized over relations which are essentially parametric relations. So these constitute an expressive type language. However, for the type-based shape analysis to be effective, we need type checking with these sort of expressive types to be decidable and practical. So the type checking, we have local type inference in so we can think of local type inference where types are annotated at the function boundaries. So we'll have to type check whether the environment provides a correct type to the function provides a correct type to the environment. So these types are refined types. So base types, the type checking between the base types is purely syntactic, whereas the type checking between refinements, since refinements have semantic interpretation, is where the decidability is a question, and these refinements need to be encodable in a decidable logic in order for the type checking to be decidable. So in the case of relational type refinements, we have an encoding into a decidable logic where the decidable logic is the effectively propositional fragment of many-sorted first-order logic. So the type checking in our system is decidable. Many-sorted first-order logic is a syntactic extension of first-order logic with sorts or types, and for the case of our encoding, we are specifically interested in effectively propositional fragment that contains the standard constructs such as uninterpreted sorts, sorted variables, sorted uninterpreted Boolean functions, or just relations. But along with these standard constructs, it also offers Phoenix quantification or sorted variables and yet remains decidable. So why do we need quantification over sorted variables? Because we talk about properties over the elements, the set of elements in the tree, all elements in the tree, or all elements in the list, and so on. So in order to quantify our elements in the tree, we require quantification, and effectively propositional logic provides premix quantification over assertions and yet remains decidable. Encoding of type refinements is defined by a function that translates artifacts of a type language into many sorted first order logic. So most constructs of a type refinement language, such as relations, types, and so on, the ML types and so on, it's straightforward to encode them in EPR fragment of MS-FOL. However, encoding parametric relations is not non-trivial because they do not exist parametric relations in first order logic. So how do we go about encoding parametric relations? We will rely on a crucial observation that a fully instantiated parametric relation can be defined in terms of its component non-parametric relations. For example, for the tree of pairs that we have seen that in-order relation of tree T is a relation that relates pairs, and parametric in-order relation where the parameter is instantiated with the RFST relation is a relation that relates first components of pairs in tree T. So observe that the set RIO RFST of T, which is a parametric in-order relation where parameter is instantiated with RFST, is obtained from the non-parametric RIO relation by mapping each component of the pair with RFST relation. In other words, we can define the parametric RIO RFST relation in terms of RFST and RIO relation by simply as a set that a set of pairs RFST A and RFST B, such that A, B belong to RIO of T, where RIO is a non-parametric in-order relation. So we can simply replace RIO RFST with the uninterpreted relation R0 and define semantics of the instantiated parametric relation as some uninterpreted relation R0, which contains a pairs of elements RFST A, RFST B, such that A, B belongs to RIO of T. So observe that this definition captures the semantics of instantiated parametric relation in terms of the non-parametric RIO and non-parametric RFST relations. There are no parametric relations in this definition. So this can be encodable straightforwardly in a decidable logic, and that's how and that defines our encoding of parametric relations in EPR fragment of MS-FOL. So we essentially introduce fresh uninterpreted relations and propositions that define these new uninterpreted relations. They define the semantics of the new uninterpreted relations in terms of existing uninterpreted relations. Right. So the EPR fragment of MS-FOL has effective decision procedures. For example, Z3 is an effective decision procedure for EPR fragment of many solid first order logic. So a practical type checker can be constructed by by straightforwardly encoding these type refinements in MS-FOL. And we did construct one such type checker. We call it getList. So getList is implemented as an extended type checking pass in Milton standard ML compiler. So getList takes a SML program with relation specifications, runs it through Milton front end, produces a core ML along with specifications, and the core ML is verified against the specification by a type checking pass to generate a relational verification condition, which is then encoded in EPR fragment of MS-FOL and then given to Z3 to either verify it or refute it. So we have used getList to verify a series of list library functions such as list library functions, reverse, concat, tree library functions such as in-order, rotate, and so on, and functional graph library functions such as traversals and so on. More importantly, we have used getList to verify certain functions in Milton compiler toolchain itself. For example, alpha renaming, substitutions, and SSA tree modification passes. So getList was able to successfully verify all these library functions as well as the compiler toolchain functions in a time span that is comparable to the actual type checking, the ML type checking pass done by Milton compiler itself. So the paper contains a few of the details that are not covered in the paper in the talk. So it contains a formal account of the core language, the relational specification language, dependent type rules, a full algorithm to compile parametric relations to EPR fragment of MS-FOL, and relational parametric types to fold the interesting higher order functions such as fold-L, fold-R, and of course more details on experiments. So I encourage you to take a look at the paper. So our compiler, our implementation of the getList is available online, so I encourage you to take a look at it as well. So that's all I have to do.
So we have time for questions.
Hello, Nikita Krylov from Chalmers. You have shown that you have an in-order relation that lets us obtain a traverse function that traverses the value respecting that relation. Does your type system allow the user to plug in his own ordering relations so the same shape can be traversed differently?
Right. So I think there are two questions. Firstly, can we introduce new relations, user-defined relations? Yes, absolutely. You can define these relations in terms of existing relations or the primitive relations recursively on the structure of data types such as trees and lists. And secondly, I think the second question is whether you have multiple implementations of in-order traversal, then the type system type check these multiple implementations.
So just to summarize with a simple example, if we have this tree shape, okay, can I traverse it in on order that I plug in?
So yeah, you could have a post-order traversal and you can still have...
So can I do tiling? That means tree value is being covered with with trees of a certain small depth, and then you traverse on the outer level between the small trees and on the inner level inside of the small trees.
Right.
Can you do that?
I think you can write up relations that are specific, that will capture your traversal, your pattern of your traversal, and those can be used to define the types to write the assertion that you require for or your type.
And I can coerce my type so I can traverse the same value differently on different occasions, right?
I see something.
Well, we can talk later.
Yeah,
thank you. That sounds cool already.
Hi, Gabriel from Inria. I was a bit confused by your parametric relations. Then later you explained that you can compile them away, so that's simpler.
Parametric relations, okay.
Yes, but then you showed an example where the parametric relation had a very specific shape, and it was clear how you compile that. Can you compile any kind of parametric relation, or do you have a restriction of the language of parametric relation that you can compile?
You mean can we do it over any trees, not just the constant trees?
No, the relations themselves that are parameters.
Oh yeah, relations can be defined as I said inductively over the structure of the data type itself. So you can write relations over infinite data structures, not just a constant ones.
So I have a question that so you generate for each data type, I guess you generate the in order, or so what is it you generate primitively for?
So primitively we only have relations such as identity, the trivial relations identity, null, equality, and so on. Whereas these kind of the relations like RFO, or in-order relation, or so on, forward order in-order relation, can be defined in terms of these primitive relations by recursing over the structure of trees.
Okay, so those are things you define.
That can be defined.
Okay, so thank you. Okay, thank you, speaker again. So the next session starts, I believe, at 3:10.